Look up at the night sky on a clear evening. The stars appear as tiny points of light, distant and unchanging. The moon glows softly. Everything seems peaceful, orderly, predictable. The cosmos looks like a vast but simple place, governed by laws we understand, filled with objects that make sense. But the more closely we study space, the stranger it becomes. The universe is not what it appears to be from our small vantage point on Earth. Out there, beyond our atmosphere, beyond our solar system, beyond our galaxy, we have discovered things that challenge everything we thought we knew about reality. Some of these discoveries are unusual, but still comprehensible. Others push the boundaries of our understanding. And a few are so strange, so fundamentally weird, that they force us to question whether the universe operates in ways we can never fully grasp. This is not a story about fear or cosmic horror. This is about wonder, about the quiet realization that we live in a universe far more mysterious and beautiful than we ever imagined. A universe where the normal rules do not always apply, where invisible forces shape galaxies, where time itself can bend and stretch, where things exist that we can detect but cannot see, measure but cannot understand. If this intrigues you, if you want to explore these cosmic mysteries together, consider liking this video and subscribing. There is so much strangeness waiting to be discovered. Let us begin our journey into the unknown. And let us start not with the most bizarre discoveries, but with something simpler, something that will gently show us that space is not quite what we thought it was. Part 1. Wandering worlds and rogue planets. When we think of planets, we imagine them orbiting stars. Mercury circles the Sun. Jupiter has its place in our solar system. Every planet we learned about in school belongs to a star, bound by gravity, following a predictable path. But in the darkness between stars, there are planets that belong to no one. They are called rogue planets, and they drift through the galaxy alone, untethered, wandering through the cosmic void, with no sun to warm them, no star to orbit. Imagine a world like Earth, but frozen, dark, and silent. No seasons, because there is no sun to create them. No days and nights as we know them, because there is no star to rise and set. Just eternal darkness and cold that goes beyond anything we can truly comprehend. Temperatures hundreds of degrees below zero. A world where any ocean would be frozen solid, where any atmosphere would condense and fall as snow. These rogue planets were not always alone. Most likely they formed around stars, just like the planets in our solar system. They had orbits once. They knew the warmth of a sun, but something happened. Perhaps they came too close to another planet, and gravity flung them outward. Perhaps two stars passed near each other, and the gravitational disruption ejected them into the void. Or maybe their star died, and they were cast adrift when the gravitational anchor disappeared. Now they travel through space, moving between the stars, journeying through regions where light is rare and darkness is absolute. How do we know these planets exist if they give off no light? We detect them through gravitational effects. When a rogue planet passes in front of a distant star, its gravity bends the starlight, creating a brief brightening that we can measure. This is called gravitational microlensing. The planet itself remains invisible, but its presence is revealed by the way it warps space around it. The first suspected rogue planet was detected in 2011. Astronomers noticed a microlensing event that lasted only about a day, far too short to be caused by a star. The calculations suggested an object with a mass similar to Jupiter, but with no star nearby. It was alone, drifting through space. Since then, astronomers have found more candidates. The exact number is uncertain because these planets are so difficult to detect. They do not emit light. They do not orbit visible stars. They pass through space silently, revealing themselves only through rare gravitational interactions. Astronomers estimate that there may be billions of rogue planets in our galaxy alone. Some studies suggest there could be twice as many rogue planets as there are stars, or even more, an entire hidden population of worlds drifting silently through the darkness, unseen and unnoticed. Think about that for a moment. Between the stars, in the vast empty spaces we think of as voids, there may be countless worlds. Some of them might be small, like Mars or Mercury. Others could be gas giants, larger than Jupiter, wandering alone through the void. And a few might even be Earth-sized, with frozen oceans beneath their icy crusts, locked away from any source of heat or light. The surfaces of these worlds would be utterly alien. On an Earth-like rogue planet, the sky would be black, not the deep blue of Earth's sky, but pure black, like the deepest cave. There would be no sun to light the landscape, no moon to reflect light, only the faint, distant stars, so far away that they provide almost no illumination. The temperature would be staggering. Without a sun to provide warmth, the surface would cool to near absolute zero. Any atmosphere would freeze and fall as snow. Water would become ice. Carbon dioxide would solidify. Only the lightest gases, like hydrogen and helium, might remain in gaseous form, and even they would be thin and cold. But beneath the surface, things might be different. Deep inside a rogue planet, there could be heat. Radioactive decay in the planet's core generates warmth, and this process continues for billions of years, independent of any external heat source. On Earth, radioactive decay contributes to the heat that drives plate tectonics and volcanic activity. On a rogue planet, it could be the only source of warmth. If a rogue planet is large enough, if it has a thick layer of ice on its surface, that ice could act as insulation. Beneath it, there might be liquid water, an ocean hidden beneath kilometers of ice, warmed from below by the planet's core. This is not just speculation. We see this on some moons in our own solar system. Europa, a moon of Jupiter, is covered in ice, but beneath that ice is an ocean of liquid water, kept warm by tidal heating. Enceladus, a moon of Saturn, has geysers that spray water into space from a subsurface ocean. A rogue planet could have the same thing, an ocean beneath the ice. And where there is liquid water, there could be life. This is a strange thought. Life on a world with no sun. Life that has never seen light. Life that exists in total darkness, sustained by chemical energy from hydrothermal vents on the ocean floor. On Earth, we have such ecosystems. Deep in the ocean, far from sunlight, there are communities of organisms that live around hydrothermal vents. These vents spew superheated water, rich in minerals and chemicals. Bacteria use these chemicals as an energy source, and other organisms feed on the bacteria. No sunlight required, no photosynthesis, just chemistry. Could the same thing happen on a rogue planet? We do not know. But the possibility is there, quiet and strange. Entire ecosystems might thrive in the dark, never knowing that stars exist, never seeing light, living in eternal night beneath kilometers of ice. And if life can exist on rogue planets, then life might be far more common in the universe than we think. We have been searching for life on planets that orbit stars. Planets in the so-called habitable zone, where temperatures allow liquid water to exist on the surface. But if life can exist beneath the ice on rogue planets, then the habitable zone is much larger. It could include any planet with enough internal heat to maintain a subsurface ocean. Rogue planets also raise questions about planetary formation. How common are they? How do they end up alone? Do they form around stars and then get ejected? Or can they form in isolation, condensing directly from clouds of gas and dust without ever having a parent star? Some astronomers think that rogue planets might form in the outer regions of planetary systems, where gravitational interactions are chaotic. Young planetary systems are violent places. Planets migrate inward and outward. They collide. They scatter each other. And sometimes, a planet gets flung out entirely, ejected from the system at high speed. But there is also evidence that some rogue planets might form on their own, without a star. In regions of space where gas and dust are collapsing to form stars, smaller clumps might condense into planet-sized objects before they can gather enough mass to ignite nuclear fusion and become stars themselves. These sub-brown dwarfs, sometimes called planetary mass objects, would be born alone, never part of a planetary system. We are only beginning to understand rogue planets. Every new detection adds to the mystery. Are they rare or common? Are they mostly gas giants, or are there rocky worlds too? Do any of them have moons? And could life exist on them? Rogue planets remind us that the universe is not as organized as we once believed. Not everything has a place. Not everything follows the rules we expect. And out there, in the spaces between the stars, entire worlds drift alone, silent witnesses to the vastness and loneliness of space. But rogue planets are only the beginning. They are strange, yes, but they are still planets. They are made of rock and ice and gas, the same materials we understand. They follow the laws of gravity and motion, even if they have no star to orbit. As we go deeper into space, we will find things that are far stranger, things that challenge not just our expectations, but the very nature of reality itself. Part 2. Neutron stars and the limits of density. Let us talk about density. On Earth, lead is dense, gold is denser. The core of our planet, made of iron and nickel, is denser still. But these are nothing compared to what exists in space. When a massive star runs out of fuel, it can no longer support itself against the crushing force of its own gravity. The core collapses. In less than a second, a region the size of Earth compresses down to a sphere only about 20 kilometers across. The atoms themselves are crushed. Electrons are forced into protons, creating neutrons. What remains is a neutron star. A neutron star is so dense that a single teaspoon of its material would weigh about 1 billion tons, more than all the cars, buildings, and ships on Earth combined, compressed into a volume smaller than a sugar cube. Imagine holding that in your hand. Of course you could not. The gravity would be so intense that it would pull you apart at the atomic level before you even got close. On the surface of a neutron star, gravity is about 200 billion times stronger than on Earth. If you could somehow stand on it, you would be flattened instantly to a layer thinner than an atom. Mountains on a neutron star, if they exist at all, would be only a few millimeters high, because gravity crushes everything down with unimaginable force. And neutron stars spin. Some of them rotate hundreds of times per second, faster than a blender blade, faster than anything we can create on Earth. And as they spin, they emit beams of radiation from their magnetic poles. If one of those beams sweeps across Earth, we detect it as a pulse of light or radio waves. These are called pulsars, and they are among the most precise clocks in the universe. The fastest known pulsar rotates 716 times per second. Imagine something the size of a city, with more mass than the sun, spinning so fast that its surface is moving at a significant fraction of the speed of light. The forces involved are beyond human comprehension. Neutron stars also have the strongest magnetic fields in the known universe. Some neutron stars, called magnetars, have magnetic fields trillions of times stronger than any magnet on Earth. These fields are so powerful that they warp the very atoms around them, stretching them into elongated shapes. If a magnetar were as close to Earth as the Moon, its magnetic field would erase every credit card, hard drive, and electronic device on the planet. It would pull the iron out of your blood. But magnetars do something even stranger. Occasionally, they experience what is called a starquake. The crust of the neutron star, under immense stress, cracks and shifts. When this happens, the magnetic field reconfigures violently, and the magnetar releases an enormous burst of energy in the form of X-rays and gamma rays. In 2004, A magnetar called SGR 1806-20 erupted. For a tenth of a second, it released more energy than the sun produces in 100,000 years. The burst of radiation traveled across the galaxy and reached Earth. It ionized part of our atmosphere and disrupted radio communications. And this happened from a star more than 50,000 light-years away. If that magnetar had been within 10 light-years of Earth, the radiation burst would have stripped away our ozone layer and caused a mass extinction. Neutron stars show us that matter can be compressed to almost unimaginable densities. They show us that the universe contains objects so extreme that our everyday experience gives us no framework for understanding them. A neutron star is not just a dense object, it is a piece of matter that has been crushed to the very edge of what physics allows. And yet, neutron stars are not the densest things in the universe. There is something even more extreme, something that takes density to its absolute limit, something from which not even light can escape. But before we go there, before we venture into the darkest and strangest corners of space, let us take a breath. Let us remember where we started. We began with rogue planets, worlds that wander alone. We moved to neutron stars, objects so dense that they redefine what matter can be. Already, space is stranger than we thought, and we have only just begun. Part 3. Black holes and the breakdown of intuition. There are places in the universe where the normal rules of reality stop working, places where time slows down, where space curves back on itself, where gravity becomes so strong that nothing, not even light, can escape. These places are called black holes, and they are among the strangest things we have ever discovered. A black hole forms when matter collapses so completely that it creates a point of infinite density called a singularity. Around this singularity is a boundary called the event horizon. If anything crosses this boundary, it is gone, forever. No signal, no information, no particle of any kind can ever escape. From the outside, a black hole looks like nothing. It does not glow, it does not emit light. It is, quite literally, a hole in space. We can only detect black holes by observing how they affect the things around them. Stars orbiting an invisible companion, gas spiraling inward and heating up to millions of degrees, the bending of light from distant galaxies. But the strangeness of black holes goes far beyond their invisibility. Black holes break our intuitive understanding of time and space. If you were to watch someone fall into a black hole, you would see something very strange. As they approach the event horizon, they would appear to slow down. Time itself, from your perspective, would be stretching for them. They would move slower and slower, their image freezing at the edge of the event horizon, never quite crossing it. You would see them fade and redden as the light from them became stretched and dimmed, but you would never see them actually disappear. But from their perspective, something very different happens. They would not feel time slowing down. To them, they would cross the event horizon in a finite amount of time, perhaps only a few seconds. And once across, they would fall toward the singularity, experiencing what is called spaghettification. The gravity at their feet would be so much stronger than at their head that they would be stretched like taffy, pulled longer and thinner until every atom in their body was torn apart. This difference in perspective is not an illusion. Time really does pass differently near a black hole. The closer you get to the event horizon, the slower time moves relative to someone far away. This is not science fiction. This is confirmed by the equations of general relativity, and it has been tested with precision experiments using atomic clocks. Black holes also raise profound questions about information. In physics, information is supposed to be conserved. If you know the state of a system now, and you know the laws of physics, you should be able to determine what the system was like in the past and what it will be like in the future. But if something falls into a black hole, that information seems to disappear. It crosses the event horizon, and is gone. This creates what is called the black hole information paradox. Does the information truly disappear, violating the laws of physics? Or is it somehow preserved, encoded in the structure of the black hole itself? Physicists have been debating this for decades, and we still do not have a complete answer. Stephen Hawking proposed that black holes are not entirely black. Through a quantum process, they can emit radiation, now called Hawking radiation, over immense timescales, far longer than the current age of the universe. A black hole could evaporate completely, releasing its mass back into space. But if the black hole evaporates, what happens to the information that fell in? Does it come back out in the radiation, scrambled beyond recognition, or is it lost forever? We do not know. And this uncertainty points to something deeper. Black holes sit at the intersection of quantum mechanics and general relativity, two theories that do not quite fit together. To fully understand black holes, we need a theory of quantum gravity, something we do not yet have. At the center of our own galaxy, there is a supermassive black hole. It is called Sagittarius A star, and it contains the mass of about 4 million suns, all compressed into a region smaller than the orbit of Mercury. We have watched stars orbit this invisible object, moving at speeds of thousands of kilometers per second, whipping around in elliptical paths that bring them terrifyingly close to the event horizon. One star, called S2, has an orbital period of about 16 years. At its closest approach to Sagittarius A star, it comes within 17 light hours of the event horizon, traveling at nearly 2% of the speed of light. We have tracked this star for decades, and its motion matches the predictions of general relativity with astonishing precision. But Sagittarius A star is not the largest black hole we have found. In the centers of distant galaxies, there are black holes billions of times more massive than the Sun. Some of them are so large that their event horizons could swallow our entire solar system. And these supermassive black holes seem to play a crucial role in the formation and evolution of galaxies. We do not yet understand exactly how or why. But the relationship between galaxies and their central black holes is one of the great mysteries of modern astronomy. Black holes show us that the universe contains places where our intuition fails completely. They are objects so extreme that they warp space and time itself, and they remind us that the cosmos operates on principles that go far beyond our everyday experience. But black holes, for all their strangeness, are at least made of matter. They are the remnants of stars, collapsed and compressed to their ultimate limit. As we go deeper into the mysteries of space, we will encounter things that are even harder to grasp, things that are not made of matter at all, things that are invisible, intangible, and yet shape the structure of the entire universe. Part 4. Dark Matter and the Invisible Universe. When astronomers measure the mass of a galaxy, they have two ways to do it. They can add up all the visible matter, the stars and gas and dust, or they can measure how fast the galaxy rotates and calculate how much mass is needed to hold it together. These two methods should give the same answer, but they do not. Galaxies rotate too fast. Based on the visible matter alone, they should be flying apart. The outer stars should be flung off into space, because there is not enough gravity to keep them in orbit. But they are not flying apart. Something is holding them together. Something we cannot see. That something is called dark matter, and it makes up about 85% of all the matter in the universe. Everything we can see, every star, every planet, every galaxy, every atom of ordinary matter accounts for only 15% of the total. The rest is dark matter, invisible and mysterious. We do not know what dark matter is. We cannot see it because it does not emit, absorb, or reflect light. It does not interact with electromagnetic radiation at all. The only way we know it exists is through its gravitational effects. It pulls on galaxies. It bends light. It shapes the large-scale structure of the universe. Imagine if 85% of everything around you was invisible. You could feel its weight. You could see how it affects other things, but you could never see it directly. That is the situation we are in with dark matter. We live in a universe dominated by something we cannot detect, except through gravity. Physicists have proposed many candidates for what dark matter might be. Maybe it is made of particles that interact very weakly with ordinary matter, so weakly that they pass through us constantly without leaving a trace. These hypothetical particles are called WIMPs, which stands for weakly interacting massive particles. Experiments deep underground are searching for them, trying to detect the rare moments when a dark matter particle might collide with an atomic nucleus. So far, they have found nothing. Or maybe dark matter is made of axions, extremely light particles that would exist in vast numbers, filling space like a cosmic fog. Or maybe it is something else entirely, something we have not thought of yet. The mystery deepens when we look at how dark matter is distributed. It does not clump together like ordinary matter. Instead, it forms vast halos around galaxies, invisible scaffolding that holds the visible stars in place. Computer simulations show that dark matter forms a cosmic web, with filaments stretching across hundreds of millions of light years, connecting galaxy clusters like threads in an enormous tapestry. This cosmic web is the skeleton of the universe. Galaxies form where the dark matter is densest. The visible universe, everything we can see, is merely decoration on a framework we cannot perceive. Dark matter also plays a crucial role in the formation of structure in the universe. In the early universe, just after the Big Bang, matter was distributed almost uniformly. There were tiny fluctuations, small differences in density from one region to another. Over billions of years, gravity amplified these fluctuations. Denser regions attracted more matter, becoming denser still, eventually forming galaxies and galaxy clusters. But ordinary matter alone could not have done this quickly enough. Radiation pressure from the Big Bang would have pushed the ordinary matter around, smoothing out the fluctuations. Dark matter, unaffected by radiation, could clump together, undisturbed. It formed the seeds around which ordinary matter could gather. Without dark matter, galaxies as we know them would not exist. And yet, we do not know what it is. We cannot touch it, cannot see it, cannot interact with it in any way except through gravity. It is a fundamental component of the universe, and it is completely mysterious. Some physicists have proposed alternative explanations. Maybe our understanding of gravity is wrong. Maybe, at very large scales, gravity works differently than we think, and there is no need for dark matter at all. These theories, collectively called modified gravity, attempt to explain the observations without invoking invisible matter. But so far, they have not been as successful as the dark matter hypothesis in explaining all the data. The existence of dark matter tells us something profound. It tells us that the universe we see is only a small fraction of what exists. Most of reality is hidden from us, invisible and unknown. We are like people living in a house who can only see one room, unaware that there are many others beyond the walls. And dark matter is not the only invisible component of the universe. There is something even stranger, something that does not just fill space, but actively pushes it apart. Part 5. Dark Energy and the Accelerating Universe. For most of human history, we assumed the universe was static and eternal. Then, in the early 20th century, astronomers discovered that the universe is expanding. Galaxies are moving away from each other, and the farther apart they are, the faster they recede. This led to the idea of the Big Bang, the theory that the universe began in an incredibly hot, dense state and has been expanding ever since. But the expansion raised a question. Gravity pulls things together, so the expansion should be slowing down over time, right? The mutual gravitational attraction of all the matter in the universe should be putting the brakes on. gradually bringing the expansion to a halt, or even reversing it. In the late 1990s, two teams of astronomers set out to measure how much the expansion was slowing down. They studied distant supernovae, explosions of stars that are so bright and so consistent that they can be used as cosmic distance markers. By measuring the light from these supernovae, they could determine how far away they were and how fast they were moving. And they discovered something shocking. The expansion is not slowing down, it is speeding up. The universe is accelerating. Something is pushing galaxies apart, overcoming the pull of gravity, causing space itself to expand faster and faster. This discovery won the Nobel Prize in Physics in 2011, and it fundamentally changed our understanding of the universe. The force driving this acceleration is called dark energy, and it is even more mysterious than dark matter. Dark energy makes up about 68% of the total energy content of the universe. Dark matter accounts for 27%. Ordinary matter, everything we can see and touch, is only 5%. We live in a universe dominated by things we do not understand. What is dark energy? We do not know. The simplest explanation is that it is a property of space itself. Empty space, according to quantum mechanics, is not truly empty. It seethes with virtual particles, popping in and out of existence, creating what is called vacuum energy. Maybe dark energy is just this vacuum energy, a constant energy density that fills all of space. But there is a problem. When physicists calculate how much vacuum energy there should be based on quantum field theory, they get a number that is vastly larger than what we observe. Not a little bit larger, not twice as large, about 10 to the power of 120 times larger. This is called the cosmological constant problem, and it is one of the biggest unsolved mysteries in physics. If vacuum energy were that large, the universe would have been torn apart almost instantly after the Big Bang. Clearly, something is wrong with our calculations, but we do not know what. Another possibility is that dark energy is not constant. Maybe it changes over time, growing stronger or weaker. This would be a dynamical field, something that evolves as the universe expands. Physicists call this quintessence. But we have no evidence for it, and we do not know what it would be made of or how it would work. Dark energy has profound implications for the future of the universe. If it continues to accelerate the expansion, galaxies will move farther and farther apart. Eventually, galaxies outside our local group will recede so fast that light from them will never reach us. The observable universe will shrink. Billions of years from now, intelligent beings in our galaxy will look out and see only darkness. All the distant galaxies will have disappeared beyond the cosmic horizon. And if dark energy grows stronger over time, the acceleration could become so extreme that it tears apart galaxies, then stars, then planets, then atoms themselves. This hypothetical end of the universe is called the Big Rip. We do not know if it will happen, but it is a possibility. Or maybe dark energy will weaken, or even reverse. Maybe the universe will stop accelerating and begin to contract, eventually collapsing in a big crunch. We simply do not know. What we do know is that the universe is not what it seems. Most of it is invisible to us. Dark matter shapes the galaxies. Dark energy drives the expansion. And we understand neither. This realization is humbling. For centuries, we thought we understood the cosmos. We mapped the stars, calculated the orbits of planets, discovered the laws of physics. But now we know that we have been studying only a tiny fraction of reality. The vast majority of the universe is made of things we cannot see, cannot touch, and do not understand. And the strangeness goes even deeper, because the universe does not just contain strange objects and invisible forces. It also behaves in ways that defy our basic intuitions about how reality should work. Part 6. Quantum Strangeness in the Cosmos. The laws of physics that govern the very small are different from the laws we experience in everyday life. At the quantum level, particles do not have definite positions or velocities until they are measured. They exist in a state of superposition, occupying multiple states at once, and they can be entangled, linked in such a way that measuring one particle instantly affects another, no matter how far apart they are. This is quantum mechanics, and it is one of the most successful theories in the history of science. It explains the behavior of atoms, the structure of molecules, the properties of light. It is the foundation of modern technology, from lasers to computer chips to MRI machines. But quantum mechanics is also deeply weird. It challenges our basic assumptions about reality. And as we look out into space, we find that this quantum weirdness is not confined to laboratories or subatomic particles. It plays a role in the cosmos itself. Consider the early universe. In the first fraction of a second after the Big Bang, the universe was incredibly hot and dense. All of space was filled with quantum fluctuations, tiny variations in energy and density. These fluctuations were random, unpredictable, the result of quantum uncertainty. But then the universe underwent a period of rapid expansion, called inflation. Space expanded faster than the speed of light, stretching those tiny quantum fluctuations to enormous scales. And when inflation ended, those fluctuations became the seeds of structure in the universe. Regions that were slightly denser than average attracted more matter, eventually forming galaxies, stars, and planets. In other words, the large-scale structure of the universe, the distribution of galaxies across billions of light years, has its origin in quantum fluctuations. The cosmic web of dark matter, the clusters and superclusters of galaxies, all of it traces back to quantum randomness in the first moments after the Big Bang. This means that the universe we see is, in some sense, the result of quantum events. The placement of galaxies is not deterministic. It is probabilistic, shaped by the inherent uncertainty of quantum mechanics. We can see the imprint of these fluctuations in the cosmic microwave background, the faint glow of radiation left over from the Big Bang. This radiation fills all of space, a relic from when the universe was only 380,000 years old. And it is not perfectly uniform. There are tiny temperature variations, differences of only a few parts in 100,000. These variations correspond to the density fluctuations that seeded the formation of galaxies. When we map the cosmic microwave background, we are looking at the quantum fluctuations of the early universe, frozen in time and blown up to cosmic scales. We are seeing the fingerprint of quantum mechanics written across the sky. But quantum mechanics also raises deeper questions. One of the most famous is the measurement problem. In quantum mechanics, a particle exists in a superposition of states until it is observed. But what counts as an observation? Does it require a conscious observer? Or does any interaction with the environment count? And what happens to the other states? If a particle can be in two places at once, and we observe it in one place, what happens to the version that was in the other place? According to one interpretation, called the many worlds interpretation, both versions continue to exist in separate, parallel universes. Every quantum measurement splits the universe into multiple branches, each one representing a different outcome. This sounds like science fiction, but it is a serious interpretation of quantum mechanics, taken seriously by many physicists. If it is true, then every time a quantum event occurs, the universe branches. There are countless parallel realities, each one slightly different, all existing simultaneously. We do not know if this is true, and we may never know, because by definition, we cannot observe these other branches. But the fact that serious scientists consider it a possibility shows how strange quantum mechanics really is. Another quantum phenomenon is entanglement. If two particles are entangled, measuring one instantly affects the other, even if they are separated by vast distances. This does not violate relativity. because no information is transmitted faster than light. But it does mean that the two particles are connected in a way that transcends space. They are not independent objects. They are part of a single quantum system. Entanglement has been demonstrated in laboratories countless times. It is real, and it is weird. And some physicists speculate that entanglement might play a role in the structure of space itself. Maybe space is not a smooth continuum, but a network of entangled quantum states. Maybe the fabric of reality is woven from quantum connections we cannot see. This is highly speculative, but it points to a deeper truth. The universe operates on principles that go far beyond our everyday experience. Quantum mechanics is not just a theory about small things. It is a fundamental description of reality, and its implications extend to the cosmos itself. Part 7. Mysterious Signals and Unexplained Phenomena. Space is full of signals. Radio waves, X-rays, gamma rays, all traveling across the void, carrying information from distant stars and galaxies. Most of these signals are understood. We know where they come from and why they exist. But some signals are strange. They appear suddenly, without warning, and disappear just as quickly. They do not repeat. They do not fit any known pattern, and we do not know what causes them. One example is fast radio bursts. These are extremely brief pulses of radio waves, lasting only a few milliseconds. They were first discovered in 2007, when astronomers noticed a strange signal in old data from a radio telescope in Australia. The signal was incredibly bright and incredibly short, and it came from far beyond our galaxy. At first, it was thought to be a fluke, maybe interference from Earth-based technology. But more fast radio bursts were found, and they all shared certain characteristics. They were extragalactic, coming from billions of light years away. They were extremely energetic, releasing as much energy in a few milliseconds as the sun does in several days. And they were not associated with any visible object. No galaxy, no star, no obvious source. For years, fast radio bursts were a complete mystery. Dozens of theories were proposed. Maybe they were caused by colliding neutron stars. Maybe they were the result of massive solar flares on distant stars. Maybe they were signals from advanced alien civilizations. We now know that at least some fast radio bursts repeat. One source, called FRB 121102, has been detected multiple times, always from the same location in space. This has allowed astronomers to study it in more detail, and they have traced it to a dwarf galaxy about 3 billion light-years away. But we still do not know what causes these bursts. The leading theory is that they are produced by magnetars, neutron stars with extremely strong magnetic fields. When a magnetar undergoes a starquake, or when its magnetic field reconfigures violently, it could release a burst of radio waves. But this is only a hypothesis. We do not have definitive proof. Another mystery is the WOW signal. In 1977, a radio telescope in Ohio detected a strong narrowband radio signal that lasted for 72 seconds. The signal was so unusual that the astronomer who found it wrote, "Wow," in the margin of the printout. The signal came from the direction of the constellation Sagittarius, and it has never been detected again. Was it a signal from an alien civilization? Probably not. The most likely explanation is that it was caused by a comet, which can emit radio waves under certain conditions. But we do not know for sure. The WOW signal remains one of the great unsolved mysteries of radio astronomy. Then there are gamma-ray bursts. These are the most energetic explosions in the universe, releasing more energy in a few seconds than the sun will produce in its entire lifetime. They were first detected in the 1960s by military satellites designed to watch for nuclear tests. The satellites picked up brief, intense flashes of gamma rays coming from space. At first, no one knew what they were. Gamma ray bursts occur randomly across the sky, with no obvious pattern. They do not repeat, and they are incredibly distant, coming from galaxies billions of light years away. We now believe that gamma-ray bursts are caused by two different processes. Short gamma-ray bursts, lasting less than 2 seconds, are thought to be the result of colliding neutron stars, or a neutron star merging with a black hole. Long gamma-ray bursts, lasting more than 2 seconds, are thought to be associated with the collapse of massive stars into black holes. But even with these theories, gamma-ray bursts are not fully understood. The exact mechanisms that produce the bursts are still being studied, and the sheer energy involved is staggering. If a gamma-ray burst occurred within our galaxy, pointed in our direction, it could strip away Earth's ozone layer and cause a mass extinction. There are also unexplained structures in space. In 2015, astronomers discovered a massive ring of galaxies about 5 billion light-years across. This structure is so large that it challenges our understanding of how the universe is organized. According to current cosmological models, there should not be structures this big. The universe should be relatively uniform on the largest scales. But this ring is anything but uniform. And there are cosmic voids, vast regions of space with very few galaxies. Some of these voids are hundreds of millions of light-years across, almost completely empty. We do not fully understand why they exist or how they formed. The universe is full of mysteries. Some of them we are beginning to solve. Others remain completely unexplained. And with every answer, new questions arise. Part 8. The limits of the observable universe. The universe is big, unimaginably big. Our galaxy, the Milky Way, contains about 200 billion stars. And there are about 2 trillion galaxies in the observable universe, each one filled with billions or trillions of stars. But the observable universe is not the entire universe. It is only the part we can see. Light from more distant regions has not had time to reach us yet, because the universe is only about 13.8 billion years old. Light from anything farther than the cosmic horizon, about 46 billion light-years away, has not had time to arrive. Beyond that horizon, the universe continues. We do not know how far it extends. It could be infinite, or it could be finite but unbounded, like the surface of a sphere curving back on itself in higher dimensions. We will never know what lies beyond the observable universe. As the universe expands, the cosmic horizon recedes, and we can see farther and farther into space. But the expansion is accelerating, driven by dark energy. Eventually, the expansion will be so fast that light from distant galaxies will never reach us. The observable universe will shrink, and we will be left in increasing isolation. But even within the observable universe, there are limits to what we can know. The farther we look, the farther back in time we see, because light takes time to travel. When we look at a galaxy 10 billion light-years away, we are seeing it as it was 10 billion years ago, not as it is today. The farthest thing we can see is the cosmic microwave background, the faint glow of radiation from when the universe was only 380,000 years old. Beyond that, the universe was opaque. It was so hot and dense that light could not travel freely. Photons were constantly absorbed and re-emitted by electrons, scattering in all directions. We cannot see past this wall of light, but we can infer what happened earlier. We have theories about the first moments of the universe, the formation of the first particles, the synthesis of the first atomic nuclei, and we can test these theories by studying the cosmic microwave background and the distribution of elements in the universe. Still, there are things we will never observe directly. The very first instant of the Big Bang, the moment of creation itself, is hidden from us. We can extrapolate backward using physics, but we hit a wall at the Planck time, about 10 to the minus 43 seconds after the beginning. Before that, our current theories break down. We need a theory of quantum gravity to go further, and we do not have one yet. The observable universe is also limited by the speed of light. We can never travel faster than light, and we can never send information faster than light. This means that even if the universe is infinite, even if there are other galaxies, other civilizations, other wonders beyond our horizon, we will never be able to reach them or communicate with them. We are confined to a bubble, a limited region of space, defined by how far light has traveled since the Big Bang. And as the universe expands, that bubble will grow in some ways and shrink in others. Distant galaxies will disappear from view, receding beyond the horizon. We will be left in an island of light, surrounded by an ever-growing ocean of darkness. This is both beautiful and lonely. Beautiful because it means the universe is vast, far larger than we can ever explore. Lonely because it means we are isolated, separated from much of reality by barriers we cannot cross. Part 9. What it all means. We have journeyed through some of the strangest discoveries in space. We started with rogue planets, worlds that drift alone through the void. We explored neutron stars, objects so dense that they defy comprehension. We ventured into black holes, places where time and space break down. We discovered that most of the universe is invisible. Dark matter holds galaxies together. Dark energy drives the expansion, and we do not know what either of them is. We saw that quantum mechanics, the physics of the very small, shapes the structure of the cosmos itself. The distribution of galaxies, the cosmic microwave background, all of it has roots in quantum fluctuations. We encountered mysterious signals, fast radio bursts and gamma-ray bursts, and unexplained phenomena that we are only beginning to understand. And we confronted the limits of what we can know. The observable universe is only a fraction of reality. Much of the cosmos is forever beyond our reach. What does all this mean? What should we take away from these discoveries? First, the universe is stranger than we thought, much stranger. Our everyday experience, our intuitions about how things should work, these are not reliable guides to the cosmos. Space operates on principles that go beyond human understanding. There are things out there that we can barely comprehend, and there are probably things we have not even imagined yet. Second, we are part of something vast. The universe is immense, ancient, and complex. We are tiny, brief, and limited, but we are also extraordinary, because we are the part of the universe that can think, that can wonder, that can ask questions and seek answers. Third, the strangeness is not something to fear. It is something to celebrate. The fact that the universe surprises us, that it confounds our expectations, that it reveals new mysteries with every discovery. This is what makes science exciting. This is what makes exploration worthwhile. We do not have all the answers. We probably never will. But we keep looking, keep questioning, keep reaching out into the unknown. And that is enough. Part 10. The beauty of the unknown. Look up at the night sky again. The stars still shine. The moon still glows. But now you know that space is not simple or predictable. You know that between those points of light, there are worlds drifting alone in the dark. You know that invisible matter shapes galaxies. You know that the universe is expanding, driven by a force we do not understand. You know that quantum mechanics, strange and counterintuitive, is woven into the fabric of reality itself. And you know that there are mysteries still waiting to be solved. Fast radio bursts, dark matter, dark energy, the nature of black holes, the limits of the observable universe. Some of these mysteries we will solve. We will build better telescopes, develop new theories, run more experiments. We will inch closer to understanding. But some mysteries may remain forever. There are limits to what we can know. The universe may be stranger than we can imagine, filled with phenomena that lie beyond the reach of human comprehension. And that is okay. Because the beauty of the universe is not in having all the answers. It is in the questions themselves. It is in the sense of wonder we feel when we look up and realize how much we do not know. The universe is strange. It is mysterious. It is beautiful. And It is waiting for us to explore. We started this journey looking at the night sky, thinking it was simple and distant. Now we end by looking at the same sky and seeing it for what it truly is, a canvas of mysteries, a reminder of how much remains unknown, an invitation to keep wondering, keep questioning, keep seeking. The strangest things in space are not just objects or phenomena. They are also the questions they inspire. What is dark matter? What is dark energy? What happens inside a black hole? Is the universe infinite? Are we alone? But we are looking, and as long as we keep looking, as long as we keep asking, the universe will keep revealing its secrets, one strange discovery at a time. Thank you for joining me on this journey through the cosmos. If you found this exploration thought-provoking, if you want to continue discovering the mysteries of space together, consider liking this video and subscribing. There are so many more wonders waiting to be found. Until next time, keep looking up, keep wondering, and remember that the universe is far stranger and more beautiful than we ever imagined. In the early days of a planetary system, when planets are still forming and migrating, gravitational interactions can be violent. Planets can be scattered like billiard balls. Some crash into their parent star. Some are ejected entirely, becoming rogues. Our own solar system may have experienced this chaos. Some models suggest that there may have been additional planets in the early solar system, planets that were ejected long ago and now wander the galaxy as rogues. We have no way to know for certain, but it is possible that somewhere out there, billions of kilometers away, there is a planet that once orbited the Sun. The study of rogue planets is still in its infancy. We have only detected a handful of candidates, and our methods are limited. Microlensing events are rare and unpredictable. We cannot study rogue planets in detail because they are too faint and too distant. But future telescopes might change that. The Nancy Grace Roman Space Telescope, scheduled to launch in the mid-2020s, will be able to detect many more rogue planets through microlensing. It will give us a better sense of how common they are and what they are made of. And as our technology improves, we might even be able to visit a rogue planet, not with humans, at least not anytime soon, but with robotic probes. Imagine landing on a world with no sun, drilling through the ice, and discovering an ocean beneath. Imagine finding life there, life that has evolved in total darkness, completely independent of any star. It would be one of the greatest discoveries in human history, and it would show us that life and planets are far more diverse and resilient than we ever imagined. Rogue planets are a reminder that space is full of surprises. They are worlds that should not exist, at least not according to our old models. And yet they do, billions of them, drifting through the dark, waiting to be found. Neutron stars represent one of the most extreme states of matter in the universe. To understand just how extreme they are, we need to think about what happens to matter under pressure. On Earth, even the densest materials have space between their atoms. Gold, lead, osmium, these are dense, but their atoms are still separated by electron clouds. If you could remove all that empty space, if you could compress Earth to the density of a neutron star, it would be about 300 meters across. The entire planet, all its mass, compressed to the size of a large building. But how does matter reach such extreme density? The answer lies in the death of massive stars. Stars are a constant battle between gravity and pressure. Gravity tries to crush the star inward. Pressure from nuclear fusion in the core pushes outward. As long as the star has fuel to burn, this balance is maintained. But when a massive star runs out of fuel, the balance tips. The core collapses. In less than a second, a region about the size of Earth shrinks down to a sphere only 20 kilometers across. The outer layers of the star, no longer supported, fall inward at speeds up to a quarter of the speed of light. When they hit the incompressible core, they bounce back, creating a shockwave that blows the star apart in a supernova explosion. What remains is the core, a neutron star, so dense that protons and electrons have been forced together, combining to form neutrons. The matter inside is unlike anything we can create or study on Earth. At the surface of a neutron star, gravity is so strong that if you dropped an object from a height of 1 meter, it would hit the surface at about 7 million kilometers per hour. The escape velocity is about half the speed of light, and the surface itself is solid, made of iron nuclei arranged in a crystalline lattice, but under such pressure that the lattice is far denser than any crystal on Earth. Below the surface, the structure becomes even stranger. As you go deeper, the density increases. Neutrons begin to drip out of the nuclei, forming a superfluid. This is a state of matter where the liquid has zero viscosity, flowing without friction, conducting heat perfectly. Deeper still, near the core, the density is so extreme that we do not fully understand what happens. Neutrons might break down into quarks, the fundamental particles that make them up, or exotic particles might form, particles that do not exist anywhere else in the universe. We simply do not know. The physics at those densities is beyond our current theories. Neutron stars also have magnetic fields. Most neutron stars have fields about 1 trillion times stronger than Earth's. But some, called magnetars, have fields 1,000 times stronger still. A magnetar's magnetic field is so powerful that it dominates the behavior of matter around it. Atoms become elongated, stretched into cigar shapes by the magnetic forces. If you were within 1,000 kilometers of a magnetar, the magnetic field would be strong enough to disrupt the molecular bonds in your body. You would not survive. Magnetars are violent. Their crusts are under immense stress from the magnetic field, and occasionally that stress becomes too great. The crust cracks in a starquake, and the magnetic field reconfigures in an instant, releasing a burst of energy. These bursts are staggering. In December 2004, a magnetar about 50,000 light-years away released a burst of gamma rays and X-rays. The burst lasted 1/10 of a second, but in that brief moment, it released more energy than the sun produces in 250,000 years. The radiation from that burst reached Earth. It ionized part of our upper atmosphere and temporarily disrupted radio communications. Satellites detected the event, and this was from a source 50,000 light-years away, across the galaxy. If that magnetar had been within 10 light-years of Earth, the burst could have caused significant damage to our atmosphere and potentially triggered a mass extinction. Pulsars, neutron stars that emit beams of radiation from their magnetic poles, are some of the most precise natural clocks in the universe. As the neutron star rotates, the beams sweep across space like a lighthouse. If one of those beams points toward Earth, we detect a pulse. The fastest known pulsar, PSR J17 48-2446, rotates 716 times per second. Think about that. An object with more mass than the Sun, compressed into a sphere only 20 kilometers across, spinning 716 times every second. The equator of this pulsar is moving at about 24% of the speed of light. Pulsars are so regular that astronomers can use them as cosmic clocks. Some pulsars are stable to within microseconds over years. They are more reliable than most atomic clocks. In fact, there have been proposals to use pulsars as a navigation system for spacecraft, a cosmic GPS based on the timing of pulses from multiple pulsars. Neutron stars also create gravitational waves. When two neutron stars orbit each other, they gradually spiral inward, releasing energy in the form of gravitational waves. Eventually, they merge, creating a kilonova, an explosion that produces heavy elements like gold and platinum. In 2017, astronomers detected gravitational waves from two merging neutron stars. This was the first time we had observed both gravitational waves and light from the same event. Telescopes around the world turned toward the source and watched as the kilonova faded over days and weeks. We saw the birth of gold, platinum, and other heavy elements forged in the collision. This discovery confirmed something astronomers had long suspected. Most of the gold in the universe, including the gold on Earth, was created in neutron star mergers. Every gold ring, every gold coin, every gold atom was born in one of the most violent events in the cosmos. Neutron stars show us that matter can exist in states far beyond what we experience on Earth. They push the boundaries of physics. They are laboratories for studying matter at extreme densities, extreme magnetic fields, extreme gravity. And they remind us that the universe contains places where the normal rules break down, where matter behaves in ways that seem impossible, where the forces are so strong that they reshape reality itself. Black holes are perhaps the most famous strange objects in space. They appear in movies, science fiction, popular culture. But the reality of black holes is stranger than most fiction. A black hole is a region of space-time where gravity is so strong that nothing can escape. Not matter, not light, not information. The boundary of this region is called the event horizon, and it marks the point of no return. If you were to approach a black hole, you would notice something odd about time. As you got closer to the event horizon, time would slow down relative to someone far away. This is not an illusion. Time actually passes more slowly in stronger gravitational fields, a prediction of Einstein's general relativity that has been confirmed by countless experiments. An observer watching you fall toward a black hole would see you slow down as you approach the event horizon. You would appear to freeze, your image getting dimmer and redder as the light from you became stretched and weakened. They would never see you actually cross the horizon. But from your perspective, nothing special happens at the event horizon. You would cross it in a finite amount of time. You would not feel any barrier or discontinuity. The only thing you would notice is that you could no longer escape. All paths lead inward toward the singularity at the center. And as you fell inward, you would experience tidal forces. The gravity at your feet would be stronger than at your head, because your feet are closer to the center of the black hole. This difference in gravity would stretch you, pulling you longer and thinner. This process is called spaghettification, and for a stellar mass black hole, it would tear you apart long before you reached the event horizon. But for a supermassive black hole, millions or billions of times the mass of the Sun, the tidal forces at the event horizon are much weaker. You could, in principle, cross the event horizon of a supermassive black hole without being torn apart. You would fall inward, deeper and deeper, toward the singularity. The singularity is a point of infinite density at the center of the black hole, or at least, that is what the equations of general relativity predict. But infinities in physics often indicate that our theories are incomplete. Most physicists believe that the singularity is not really a point of infinite density, but rather a region where quantum effects become important and our current understanding breaks down. What happens at the singularity? We do not know. We need a theory of quantum gravity to describe it, and we do not have one yet. String theory and loop quantum gravity are candidates, but neither has been confirmed. Black holes also raise profound questions about the nature of information. In quantum mechanics, information is conserved. If you know the quantum state of a system at one time, you can, in principle, calculate its state at any other time. But if information falls into a black hole, it seems to disappear. This violates the principle of information conservation and creates what is called the black hole information paradox. Stephen Hawking proposed a partial solution in the 1970s. He showed that black holes are not entirely black. Through a quantum process involving virtual particles near the event horizon, black holes emit radiation. This radiation, now called Hawking radiation, carries energy away from the black hole, causing it to slowly evaporate. But here is the problem. Hawking radiation, as originally calculated, is thermal. It is random, containing no information about what fell into the black hole. So if a black hole evaporates completely, the information that fell in seems to be lost forever. This led to decades of debate. Some physicists argued that information is indeed lost, and we need to revise quantum mechanics. Others argued that the information is somehow encoded in the Hawking radiation, but in a way we do not yet understand. Others suggested that the information is stored on the event horizon itself, in a kind of holographic encoding. In 2004, Hawking conceded that information is probably not lost. He proposed that it escapes in subtle correlations in the Hawking radiation, but the exact mechanism is still debated, and the black hole information paradox remains one of the great unsolved problems in theoretical physics. Black holes come in different sizes. Stellar mass black holes, formed from the collapse of massive stars, have masses between about 3 and a few dozen times the mass of the Sun. Supermassive black holes, found at the centers of galaxies, have masses ranging from millions to billions of solar masses. There is also evidence for intermediate mass black holes, with masses between about 100 and 100,000 solar masses. These are harder to detect, but astronomers have found a few candidates, and there may be primordial black holes formed in the early universe, shortly after the Big Bang. These could have any mass, from microscopic to stellar. If they exist, they might even account for some or all of the dark matter. But we have no confirmed detections of primordial black holes yet. The largest known black hole is TON 618, located in a quasar about 10 billion light-years away. It has a mass of about 66 billion times the mass of the Sun. The event horizon of this black hole is about 1,300 times the distance from the Sun to Earth. It is larger than our entire solar system. How do supermassive black holes form? We do not know for certain. They are found at the centers of most large galaxies, including our own Milky Way. But how they grew to such enormous sizes is still a mystery. They may have formed from the collapse of massive gas clouds in the early universe, or they may have grown by accreting matter and merging with other black holes over billions of years, or both. The relationship between galaxies and their central black holes is also mysterious. There is a tight correlation between the mass of a supermassive black hole and the properties of its host galaxy. Galaxies with more massive bulges tend to have more massive black holes. But why? Does the black hole influence the formation of the galaxy, or does the galaxy determine the size of the black hole? We do not yet know. In 2019, the Event Horizon Telescope collaboration released the first image of a black hole. It showed the supermassive black hole at the center of the galaxy M87, about 55 million light-years away. The image showed a dark shadow surrounded by a bright ring of glowing gas. The shadow is the black hole itself, or more precisely, it is the region where light cannot escape. The bright ring is the accretion disk, a swirling disk of gas spiraling into the black hole. The gas is heated to billions of degrees by friction and magnetic fields, causing it to glow brightly. This image confirmed many predictions of general relativity. The size and shape of the shadow matched theoretical calculations. It was a triumph of astronomy and a testament to the power of black holes to warp space and light. Black holes also serve as cosmic particle accelerators. Near the event horizon, particles can be accelerated to nearly the speed of light. Some black holes, particularly those in active galactic nuclei, produce jets of matter and energy that shoot outward at relativistic speeds, extending for thousands of light-years. These jets are among the most powerful phenomena in the universe. They are driven by the rotation of the black hole and the magnetic fields in the accretion disk. The exact mechanism is still being studied, but the results are spectacular. Jets, from supermassive black holes can influence the evolution of entire galaxies, heating the surrounding gas and regulating star formation. Black holes challenge our understanding of reality. They are places where space-time curves so severely that it wraps back on itself, where time and space swap roles, where the normal rules of cause and effect break down. And they remind us that the universe contains extremes we can barely imagine, places where the laws of physics are pushed to their limits, where our intuitions fail and our theories struggle to keep up. Dark matter remains one of the greatest mysteries in science. We know it exists, we can measure its effects, but we cannot see it, cannot touch it, cannot detect it directly. The evidence for dark matter comes from many different observations. Galaxy rotation curves show that galaxies spin too fast for the visible matter alone to hold them together. Gravitational lensing, the bending of light by massive objects, reveals that there is far more mass in galaxy clusters than we can account for with stars and gas alone. The cosmic microwave background, the afterglow of the Big Bang, shows patterns that can only be explained if dark matter exists. All of these independent lines of evidence point to the same conclusion. The universe is full of invisible matter, and this matter is not made of atoms. It is something else entirely. One of the leading candidates for dark matter is a particle that interacts only through gravity and possibly the weak nuclear force. These particles would pass through ordinary matter almost without interacting at all. Billions of them could be passing through your body right now, and you would never know. Experiments to detect dark matter have been running for decades. They typically involve large tanks of liquid placed deep underground, shielded from cosmic rays and other background radiation. The idea is to wait for a dark matter particle to collide with an atomic nucleus in the tank, producing a tiny flash of light or heat. But so far, these experiments have found nothing, or at least nothing conclusive. There have been a few anomalous signals, hints that might be dark matter or might be background noise, but no definitive detection. This is frustrating for physicists. They know dark matter is out there. They can see its effects on galaxies and the large-scale structure of the universe, but they cannot catch it. Another possibility is that dark matter is made of axions, extremely light particles that would exist in vast numbers. Axions were originally proposed to solve a problem in particle physics, but they also happen to be a good dark matter candidate. They would clump together in ways similar to what we observe, and they would not emit light. Experiments to detect actions work differently from WIMP detectors. They use strong magnetic fields to try to convert actions into photons, which can then be detected. These experiments are ongoing, and some have claimed tentative detections, but nothing has been confirmed. There are also more exotic proposals. Maybe dark matter is made of primordial black holes, tiny black holes formed in the early universe. Maybe it is made of particles from higher dimensions, leaking into our three-dimensional universe. Maybe it is something we have not even thought of yet. Dark matter is not distributed uniformly. It forms halos around galaxies, spherical or ellipsoidal clouds that extend far beyond the visible stars. Our own galaxy is embedded in a dark matter halo that extends hundreds of thousands of light years from the center. This halo is not static. It is constantly being disturbed by the infall of smaller galaxies and dark matter clumps. Simulations show that dark matter halos are filled with substructure, smaller clumps and streams of dark matter that have been pulled apart by tidal forces. And dark matter plays a crucial role in the cosmic web, the large-scale structure of the universe. Galaxies are not distributed randomly. They are organized into filaments and sheets, separated by vast voids. This structure is determined by dark matter. In the early universe, dark matter clumped together first, forming the gravitational wells into which ordinary matter fell. Over billions of years, this led to the formation of galaxies and galaxy clusters, all connected by filaments of dark matter stretching across hundreds of millions of light years. The cosmic web is mostly invisible. We can only see the galaxies, the bright nodes where ordinary matter has accumulated. But the dark matter forms the skeleton, the underlying structure that holds everything together. And yet, we do not know what it is. This is humbling. 85% of the matter in the universe is completely mysterious. We live in a cosmos dominated by something we cannot understand. Dark energy is even more mysterious. It makes up about 68% of the total energy content of the universe, and we have no idea what it is. The discovery of dark energy was a shock. In the late 1990s, two teams of astronomers were studying distant supernovae, trying to measure how much the expansion of the universe was slowing down. But instead of slowing, they found that the expansion was speeding up. This was unexpected. Gravity should be pulling things together, slowing the expansion. But something was pushing galaxies apart, overcoming gravity, causing space itself to expand faster and faster. This force is called dark energy, and it is unlike anything else we know. It does not clump like matter. It does not dilute as the universe expands. It appears to be a property of space itself, a constant energy density that fills the universe. One explanation is that dark energy is vacuum energy, the energy of empty space predicted by quantum mechanics. According to quantum field theory, even empty space is filled with virtual particles, constantly popping in and out of existence. These particles create a sort of background energy, a cosmological constant. But there is a problem. When physicists calculate how much vacuum energy there should be, they get a number that is vastly larger than what we observe. This discrepancy is one of the biggest unsolved problems in physics, and it suggests that our understanding of quantum mechanics or gravity, or both, is incomplete. Another possibility is that dark energy is not constant. Maybe it is a field that changes over time, growing stronger or weaker as the universe evolves. This is called quintessence, and it would have different effects on the expansion of the universe than a cosmological constant. Observations so far are consistent with a cosmological constant, a fixed energy density that does not change. And we do not know why it has the value it does. Dark energy has profound implications for the future of the universe. If it continues to drive the expansion, galaxies will move farther and farther apart. Eventually, all galaxies outside our local group will recede beyond the cosmic horizon, disappearing from view. The observable universe will shrink, leaving us isolated in an island of light surrounded by darkness. And if dark energy grows stronger, it could tear apart galaxies, stars, planets, even atoms. This is called the Big Rip, a hypothetical end where the universe is ripped apart by runaway acceleration. Or maybe dark energy will weaken or reverse, allowing gravity to take over and pull the universe back together in a big crunch. We do not know. The fate of the universe depends on the nature of dark energy, and we do not understand it. Quantum mechanics adds another layer of strangeness to the cosmos. At the quantum level, particles do not behave like solid objects. They exist in superpositions, occupying multiple states at once. They are entangled, linked across vast distances in ways that seem to defy our understanding of space and time. And quantum mechanics plays a role in the universe itself. The large-scale structure we see today, the distribution of galaxies, has its roots in quantum fluctuations in the early universe. In the first fraction of a second after the Big Bang, the universe was incredibly small and dense. Quantum mechanics dominated. Tiny fluctuations in energy and density arose randomly, the result of quantum uncertainty. Then the universe underwent inflation, a period of exponential expansion. Space expanded faster than the speed of light, stretching those quantum fluctuations to enormous scales. When inflation ended, the fluctuations became classical. They were no longer quantum. They were real variations in the density of matter and energy. And over billions of years, gravity amplified these variations, turning them into galaxies and galaxy clusters. So the cosmic web, the vast structure of the universe, originated from quantum randomness. The universe is, in a sense, a quantum fluctuation made real. We can see evidence of this in the cosmic microwave background. The tiny temperature variations in this ancient light correspond to the density fluctuations that seeded galaxy formation, and the statistical properties of these variations match the predictions of quantum mechanics. This is profound. It means that the universe we see is not deterministic. It is probabilistic. The exact arrangement of galaxies is the result of quantum randomness, amplified to cosmic scales. There are also mysterious signals that we do not fully understand. Fast radio bursts are one example. These are brief, intense pulses of radio waves from distant galaxies. They last only milliseconds, but they release as much energy as the sun does in days. The first fast radio burst was discovered in 2007. Since then, hundreds have been detected, and we are beginning to understand them better. Some repeat, allowing us to study them in detail. Others occur only once. The leading theory is that they are produced by magnetars, neutron stars with extremely strong magnetic fields. But we are not certain. The exact mechanism is still being investigated. Then there are gamma-ray bursts, the most energetic explosions in the universe. These release more energy in seconds than the sun will produce in its entire lifetime. They are visible across billions of light years. Gamma-ray bursts come in two types. Short bursts, lasting less than 2 seconds, are thought to be caused by merging neutron stars. Long bursts, lasting more than 2 seconds, are associated with the collapse of massive stars into black holes. But the details are still uncertain. Gamma-ray bursts involve extreme physics, and we are only beginning to understand them. The universe also contains unexplained structures. In 2015, astronomers discovered a ring of galaxies about 5 billion light-years across. This is so large that it challenges our understanding of cosmology. According to our models, the universe should be roughly uniform on the largest scales. But this structure is anything but uniform. And there are cosmic voids, vast regions with very few galaxies. Some are hundreds of millions of light-years across, almost completely empty. We do not fully understand why they exist or how they formed. The observable universe has limits. We can see out to a distance of about 46 billion light-years, but beyond that, light has not had time to reach us. The universe may extend infinitely in all directions, or it may be finite but unbounded, curving back on itself in higher dimensions. We will never know what lies beyond the observable universe. And as the universe continues to expand, driven by dark energy, the observable universe will shrink. Distant galaxies will disappear beyond the horizon, leaving us increasingly isolated. The farthest thing we can see is the cosmic microwave background, the afterglow of the Big Bang. This light has been traveling for over 13 billion years, reaching us from a time when the universe was only 380,000 years old. Before that, the universe was opaque. Light could not travel freely. It was scattered by free electrons, bouncing around in all directions. We cannot see past this wall of light. But we can infer what happened earlier. We have theories about the first moments of the universe, the formation of particles, the synthesis of elements. And we can test these theories by studying the cosmic microwave background and the distribution of matter. Still, there are things we will never observe directly. The very first instant of the Big Bang is hidden from us. Our current theories break down at the Planck time, about 10 to the minus 43 seconds after the beginning. To go further, we need a theory of quantum gravity, and we do not have one yet. What does all this strangeness mean? What should we take away from these discoveries? First, the universe is far stranger than we thought. Dark matter, dark energy, Quantum mechanics, black holes, rogue planets, all of these challenge our intuitions and force us to rethink what we know about reality. Second, we are part of something vast and mysterious. The universe is immense, ancient, and filled with things we do not understand. But we are also extraordinary, because we are the part of the universe that can think, wonder, and seek answers. Third, the strangeness is not something to fear. It is something to celebrate. The universe surprises us. It confounds our expectations. And that is what makes exploration worthwhile. We do not have all the answers. We probably never will. But we keep looking, keep questioning, keep reaching out into the unknown. And that is enough. The universe is strange. It is mysterious. It is beautiful. And it is waiting for us to explore. When we look at the history of astronomy, we see a pattern. Every time we develop a new way of observing the universe, we discover things we did not expect. The telescope revealed moons around Jupiter and phases of Venus, challenging the geocentric model. Spectroscopy revealed that stars are made of the same elements as Earth. Radio telescopes discovered pulsars and quasars. X-ray telescopes found black holes and neutron stars. Each new window into the universe has revealed new mysteries, and many of those mysteries remain unsolved. Rogue planets were not predicted. Before we had the technology to detect them through microlensing, most astronomers assumed that planets always orbited stars. The idea of billions of worlds drifting alone through space was not part of mainstream thinking. But now, we know they exist. And this has changed how we think about planetary systems. It has opened up new possibilities for where life might exist. And it has shown us that the universe is more diverse than we imagined. Neutron stars were predicted theoretically before they were observed. In the 1930s, physicists realized that if a star's core collapsed, it could form an object made entirely of neutrons. But it seemed like a wild idea, almost too extreme to be real. Then, in 1967, Jocelyn Bell Burnell discovered pulsars. At first, the signals were so regular that there was speculation they might be artificial, signals from an alien civilization. But further observations showed they were natural, coming from rotating neutron stars. The discovery of pulsars confirmed that neutron stars exist, and it opened up a new field of study. Today, we use pulsars to test general relativity, to search for gravitational waves, to study the structure of matter at extreme densities. Black holes were also predicted theoretically. Carl Schwarzschild found the first solution to Einstein's equations that described a black hole just months after Einstein published general relativity. But for decades, most physicists thought black holes were mathematical curiosities, not real objects. It was not until the 1960s and 70s that evidence for black holes began to accumulate. X-ray telescopes detected binary systems where a visible star was orbiting an invisible companion, losing mass to it. The companion was too massive to be a neutron star. It had to be a black hole. And then, astronomers found evidence for supermassive black holes at the centers of galaxies. Stars near the center of the Milky Way were observed orbiting an invisible object with millions of times the mass of the Sun. The only explanation was a supermassive black hole. Today, black holes are accepted as real and common, but it took decades of observation and theoretical work to reach that point. Dark matter is different. We did not predict it. We stumbled upon it by accident. In the 1930s, Fritz Zwicky noticed that galaxy clusters seemed to contain far more mass than could be accounted for by visible stars. He proposed that there must be dark matter, unseen mass holding the clusters together. But his idea was largely ignored for decades. It was not until the 1970s, when Vera Rubin measured the rotation curves of galaxies and found the same discrepancy, that dark matter became widely accepted. And now, dark matter is a cornerstone of cosmology. We know it exists. We can measure its effects. but we do not know what it is. Decades of searching have yielded no direct detection. And this is frustrating, but also humbling. It reminds us that we do not understand the universe as well as we might like to think. Dark energy is even more surprising. No one expected the expansion of the universe to be accelerating. When the discovery was announced in 1998, it shocked the scientific community. Gravity should slow the expansion. That is what everyone thought. But observations of distant supernovae showed the opposite. The universe was expanding faster and faster. This discovery earned the Nobel Prize, but it also created a crisis in cosmology. We do not know what dark energy is. We do not know why it has the value it does, and we do not know what it means for the future of the universe. These discoveries tell us something important. The universe does not care about our expectations. It is what it is, regardless of what we think it should be. And our job as scientists, as explorers, is to observe, to measure, to understand. We build models. We make predictions. But we must also be willing to revise those models when the evidence demands it. This is the heart of the scientific method, and it is what has allowed us to make progress, even when the universe surprises us. The psychology of strangeness. Why are we drawn to the strange? Why do we find dark matter and black holes and rogue planets so fascinating? Part of it is curiosity. Humans are naturally curious. We want to understand the world around us. And when we encounter something we do not understand, we want to figure it out. But there is also something deeper. Strangeness challenges our assumptions. It forces us to think in new ways. It reminds us that the universe is bigger and more complex than our everyday experience. When we learn that most of the universe is invisible, made of dark matter and dark energy, it is humbling. We thought we understood the cosmos. We had mapped the stars, calculated the orbits of planets, discovered the laws of physics. But now we know that we have been studying only a tiny fraction of reality. This can be unsettling. It can make us feel small and insignificant. But it can also be liberating, because it shows us that there is so much more to learn, so many mysteries still waiting to be solved, and strangeness connects us to something larger than ourselves. When we contemplate the vastness of space, the billions of galaxies, the trillions of stars, we are reminded that we are part of a universe that extends far beyond our little corner of existence. This perspective is valuable. It helps us see beyond our immediate concerns, beyond the day-to-day struggles of life. It reminds us that we are part of something much bigger, something ancient and mysterious and beautiful. But strangeness also has practical value. Every time we discover something unexpected, it pushes us to develop new theories, new technologies, new ways of thinking. The discovery of pulsars led to tests of general relativity that confirmed the theory with incredible precision. The discovery of dark matter led to new particle physics theories and new experiments. The discovery of dark energy has forced cosmologists to rethink the nature of space and time. Strangeness drives progress. It keeps us from becoming complacent. It ensures that science remains dynamic, always evolving, always seeking new answers. The role of technology. None of these discoveries would have been possible without technology. We cannot see dark matter or dark energy directly. We cannot visit neutron stars or black holes. We rely on instruments to extend our senses, to show us things that are invisible to the naked eye. The telescope was the first great instrument of astronomy. It allowed us to see the moons of Jupiter, the rings of Saturn, the phases of Venus. It revealed that the Milky Way is made of countless stars, and it showed us that the universe extends far beyond what we can see with our eyes alone. Spectroscopy, the study of light broken into its component wavelengths, revolutionized astronomy in the 19th century. It allowed us to determine what stars are made of, how hot they are, how fast they are moving. It revealed that the universe is expanding. And it showed us that the elements in stars are the same as the elements on Earth. Radio telescopes opened a new window on the universe in the 20th century. They detected emissions from objects that are invisible in visible light. They discovered pulsars, quasars, the cosmic microwave background. And they showed us that the universe is far more active and dynamic than we had imagined. X-ray and gamma-ray telescopes revealed even more. They detected black holes, neutron stars, gamma-ray bursts. They showed us the most energetic and violent phenomena in the cosmos. And they forced us to confront the extremes of physics, where our everyday intuitions break down. Gravitational wave detectors, a new tool developed in the 21st century, have opened yet another window. They detect ripples in space-time caused by colliding black holes and neutron stars. They allow us to observe events that are invisible in light, and they have confirmed predictions of general relativity that were made over a century ago. Each new technology reveals new aspects of the universe, and each new discovery raises new questions. What will the next generation of telescopes reveal? The James Webb Space Telescope, launched in 2021, is already showing us the most distant galaxies ever observed. Galaxies that formed when the universe was only a few 100 million years old. It is peering into the atmospheres of exoplanets, searching for signs of life, and it is studying the formation of stars and planetary systems in unprecedented detail. Future telescopes will be even more powerful. The extremely large telescope, under construction in Chile, will have a mirror 40 meters across, allowing it to see fainter and more distant objects than ever before. The Square Kilometer Array, a network of radio telescopes spread across 2 continents, will be the most sensitive radio telescope ever built. And there are proposals for telescopes in space, far from the interference of Earth's atmosphere. Telescopes that could detect the faint signatures of dark matter particles. Telescopes that could study the cosmic microwave background in exquisite detail. Telescopes that could search for signs of life on distant planets. With each new instrument, we will discover new mysteries. And with each new mystery, we will be reminded that the universe is stranger and more wonderful than we ever imagined. The interconnectedness of discovery. One of the remarkable things about astronomy is how interconnected the discoveries are. Dark matter affects the formation of galaxies. Black holes influence the evolution of galaxies. Neutron stars produce the heavy elements that make up planets and life. Everything in the universe is connected, and understanding one phenomenon often requires understanding others. For example, to understand how galaxies form, we need to understand dark matter. Dark matter provides the gravitational scaffolding around which galaxies assemble. Without dark matter, galaxies as we know them would not exist. But dark matter is also influenced by the large-scale structure of the universe. The cosmic web, the filaments and voids that stretch across hundreds of millions of light-years, is shaped by dark matter. And the cosmic web, in turn, determines where galaxies form. Black holes play a role too. Supermassive black holes at the centers of galaxies can regulate star formation. When they are actively feeding, they produce jets and winds that heat the surrounding gas, preventing it from cooling and forming new stars. This feedback affects the growth of the galaxy and the black hole itself. Neutron stars contribute to the chemical evolution of the universe. When 2 neutron stars merge, they produce heavy elements like gold and platinum. These elements are ejected into space, enriching the interstellar medium. Eventually, they are incorporated into new stars and planets. The gold in your jewelry was forged in a neutron star collision billions of years ago. Even quantum mechanics plays a role. The fluctuations that seeded the formation of galaxies were quantum in nature, and quantum effects may be important in the cause of neutron stars and the singularities of black holes, though we do not yet fully understand how. All of these phenomena are intertwined. To understand the universe, we cannot study one thing in isolation. We must consider the whole system. the vast web of connections that links everything together. This is both challenging and beautiful. Challenging because it means that understanding any one phenomenon requires understanding many others. Beautiful because it reveals a deep unity in nature, a coherence that underlies the apparent diversity of the cosmos. The humility of ignorance. One of the most important lessons from these discoveries is humility. We do not know everything. In fact, we know very little. We do not know what dark matter is. We do not know what dark energy is. We do not know what happens inside a black hole. We do not know if there is life on rogue planets. We do not know how supermassive black holes form. We do not know what lies beyond the observable universe. These are not small gaps in our knowledge. They are fundamental mysteries that go to the heart of what the universe is and how it works. And this is okay. Science is not about having all the answers. It is about asking the right questions and being honest about what we do not know. In fact, acknowledging our ignorance is a strength, not a weakness. It keeps us humble. It reminds us that the universe is bigger and stranger than we can fully comprehend. And it motivates us to keep exploring, keep questioning, keep seeking. The history of science is filled with examples of things we once thought we understood, only to discover that we were wrong. We thought the Earth was the center of the universe. We thought time was absolute. We thought space was flat and unchanging. We were wrong about all of these things. And we will probably be wrong about some of the things we believe today. But that is how progress happens. We make observations, we build models, we test those models, and we revise them when the evidence demands it. This process is never finished. There will always be new mysteries, always new questions. And that is what makes science exciting. The final reflection. We have journeyed through some of the strangest things in space. Rogue planets drifting alone through the void. Neutron stars so dense that a spoonful weighs billions of tons. Black holes where time and space break down. Dark matter that makes up most of the universe but remains invisible. Dark energy driving the universe apart. Quantum mechanics shaping the cosmos. Mysterious signals we do not understand. Limits to what we can know. These discoveries show us that the universe is far stranger than we thought. They challenge our intuitions. They force us to think in new ways. And they remind us that we are part of something vast and mysterious. But they also show us something else. They show us that we are capable of understanding, at least in part. We can detect dark matter through its gravitational effects. We can observe black holes by watching how they affect light and matter. We can study neutron stars through the pulses they emit. We can measure the expansion of the universe and infer the existence of dark energy. We are limited. We cannot see everything. We cannot know everything. But we can observe, we can measure, we can think, we can understand. And that is remarkable. We are the part of the universe that can contemplate itself. We are made of atoms forged in stars, organized into structures complex enough to wonder about our origins. We are the cosmos becoming aware of itself. This is a profound realization, and it gives meaning to our explorations. We are not separate from the universe. We are part of it. And when we study space, we are studying ourselves. The strangeness of the universe is not something to fear. It is something to celebrate, because it shows us that reality is richer, deeper, more mysterious than we ever imagined. And it invites us to keep exploring, to keep asking questions, to keep seeking answers. The universe is strange, and that is beautiful. When we think about the strangeness of space, we must also think about time. The universe is not just vast in space, it is also vast in time. And the timescales involved are almost incomprehensible. The universe is about 13.8 billion years old. This is a number so large that it is hard to grasp. To put it in perspective, If the entire history of the universe were compressed into a single year, with the Big Bang happening on January 1st, modern humans would appear only in the last few minutes before midnight on December 31st. All of recorded human history, everything from the invention of writing to the present day, would occur in the last second of the year. This puts our existence into perspective. We are incredibly recent. The universe existed for over 99.9% of its history without us. Stars were born and died. Galaxies formed and evolved. Black holes grew. Dark matter shaped the cosmic web. All of this happened long before humans ever looked up at the sky and wondered what was out there. And the universe will continue long after we are gone. The sun will burn for another 5 billion years. The Milky Way will eventually merge with the Andromeda Galaxy in about 4 billion years, creating a new, larger galaxy. Stars will continue to form for trillions of years, though at an ever-decreasing rate as the supply of gas and dust is exhausted. Eventually, in the far future, the universe will enter what is called the degenerate era. All the stars will have burned out. The universe will be populated by white dwarfs, neutron stars, and black holes, slowly cooling in the darkness. And even these remnants will not last forever. White dwarfs will fade to black dwarfs. Neutron stars will cool, and black holes, through Hawking radiation, will slowly evaporate. This process takes an unimaginably long time. A solar mass black hole would take about 10 to the power of 67 years to evaporate completely. In the end, the universe will be filled with nothing but elementary particles, photons, neutrinos, scattered across an ever-expanding space. This is the heat death of the universe, the final equilibrium where no energy gradients remain to drive processes. This timeline is speculative, based on our current understanding of physics. It could be wrong. Maybe dark energy will grow stronger, tearing apart galaxies, stars, and atoms in a big rip. Maybe the expansion will reverse, pulling everything back together in a big crunch. Maybe there are processes we do not yet understand that will change the course of cosmic evolution. But regardless of the details, the timescales involved are staggering. The universe has a deep past and a deep future, and we exist in a brief moment in between. This is both humbling and awe-inspiring. Humbling because it shows how small we are in the vast sweep of cosmic time. Awe-inspiring because it shows that we are part of a story that is much larger than ourselves. Carl Sagan famously spoke of the pale blue dot, the image of Earth taken from billions of kilometers away by the Voyager 1 spacecraft. In that image, Earth is a tiny speck, barely visible, suspended in a beam of sunlight. Sagan reflected on what that image means. Every person who has ever lived, every civilization, every war, every discovery, every moment of joy and sorrow, all of it happened on that tiny dot. And from the perspective of the cosmos, that dot is insignificant, a mote of dust in a vast ocean of space. This perspective is important. It reminds us of our place in the universe. We are small, we are brief, we are fragile, and the universe does not care about us. It will continue long after we are gone, indifferent to our existence. But this is not a cause for despair, because even though we are small, we are also extraordinary. We are the part of the universe that can think, that can understand, that can ask questions and seek answers. We are made of atoms forged in the cores of stars. We are made of the same stuff as galaxies, as planets, as nebulae. We are not separate from the cosmos. We are part of it, and we have achieved remarkable things. We have decoded the structure of DNA. We have sent spacecraft to other planets. We have built telescopes that can see across billions of light years. We have developed theories that describe the behavior of matter and energy, from the smallest quarks to the largest galaxy clusters. We have looked at the universe and understood, at least in part, what it is and how it works. And that is extraordinary. The cosmic perspective also reminds us of what is important. In the grand scheme of the universe, our petty conflicts and divisions seem small. The things we argue about, the things we fight over, they do not matter on cosmic scales. But the things we create, the knowledge we gain, the beauty we appreciate, these things matter. They are what make us human, and they are what give meaning to our existence. We will not last forever. Our civilization will eventually end, whether through natural disaster, self-destruction, or simply the passage of time. The sun will die, the earth will be destroyed, and eventually the universe itself will fade into darkness. But that does not make our existence meaningless, because we are here now. We are part of the universe, and we have the opportunity to understand it, to appreciate it, to marvel at its strangeness and beauty. That is enough. The ongoing search. The search for understanding is never finished. Every answer leads to new questions. Every discovery reveals new mysteries. We know that it is expanding. We know that it is filled with galaxies, stars, planets. We know that it is governed by laws of physics that we can describe mathematically. But we also know that we do not understand most of it. Dark matter, dark energy, the nature of black holes, the origin of the universe, the possibility of life beyond Earth. All of these remain mysteries. And this is okay, because the search itself is valuable. It is what drives us forward. It is what makes science exciting. Every generation of astronomers discovers something new. The generation before ours discovered the cosmic microwave background, the expansion of the universe, the existence of black holes and neutron stars. Our generation has discovered dark energy, exoplanets, gravitational waves. The next generation will discover things we cannot even imagine yet. And with each discovery, our understanding deepens. We do not just accumulate facts. We build theories, frameworks that allow us to see connections, to understand why things are the way they are. But we must also remain humble. The universe has surprised us before, and it will surprise us again. We must be willing to revise our theories when the evidence demands it. We must be open to the possibility that we are wrong. This is the heart of the scientific method. Observe, hypothesize, test, revise, and repeat. It is a process without end, a journey without a final destination. But it is a journey worth taking, because along the way, we learn, we grow, we understand, and we marvel at the strangeness and beauty of the cosmos. The question of meaning. What does it all mean? What should we take away from these discoveries? Different people will have different answers. For some, the vastness and strangeness of the universe is evidence of a creator, a divine intelligence that designed it all. For others, it is evidence of the opposite, that the universe is a natural phenomenon governed by impersonal laws. Science cannot answer these questions. Science deals with the how, not the why. It can tell us how galaxies form, how stars shine, how black holes work, but it cannot tell us why the universe exists or what our purpose is. Those are philosophical questions, questions of meaning and value, and they are important. But they are not scientific questions. What science can tell us is that the universe is vast, ancient, and strange. It is filled with wonders we are only beginning to understand, and we are part of it. We are not separate from the cosmos. We are made of its substance. We are governed by its laws. We are products of its history, and we have the capacity to understand it, to observe, to measure, to theorize, to discover. This is our gift, and it is our responsibility. We are the universe becoming aware of itself, and that is a remarkable thing. So what does it mean? Perhaps it means that we should appreciate what we have, the brief moment of existence we are given, the opportunity to learn, to explore, to wonder. Perhaps it means that we should be humble, recognizing that we are small, that we do not know everything, that the universe is bigger and stranger than we can fully comprehend. And perhaps it means that we should keep looking, keep asking questions, keep seeking answers, because the search itself is meaningful. The universe is strange, and that is beautiful, and it is waiting for us to explore. Some people ask, why study space? Why spend resources on telescopes and spacecraft when there are problems here on Earth that need solving? It is a fair question, and there are practical answers. First, the technologies developed for space exploration often have applications here on Earth. GPS satellites, for example, rely on general relativity to function correctly. Medical imaging technologies were developed using principles from astronomy. Material science, computer technology, communication systems, all have benefited from space research. But there is a deeper answer. The study of space expands our horizons. It shows us what is possible, and it inspires us to think beyond our immediate concerns. When we look at images of distant galaxies, when we learn about black holes and neutron stars, when we contemplate the vastness of the universe, we are reminded that there is more to existence than our day-to-day struggles. This perspective is valuable. It helps us see the bigger picture. It reminds us that we are part of something larger, and it inspires us to ask big questions, to pursue ambitious goals, to reach beyond what we think is possible. Many of the scientists and engineers who work on space missions were inspired by the wonders of the cosmos. They looked up at the stars as children and wondered what was out there, and that curiosity drove them to pursue careers in science and engineering. This inspiration is not just for scientists. It is for everyone. Because when we learn about the universe, when we see the beauty and strangeness of space, we are reminded of the power of human curiosity and ingenuity. We are capable of remarkable things. We can build telescopes that see across billions of light years. We can send spacecraft to other planets. We can decode the secrets of the cosmos. And this is inspiring. It shows us what we can achieve when we work together, when we apply our intelligence and creativity to big problems. So the study of space is valuable not just for the practical technologies it produces, but for the inspiration it provides. It reminds us of what we are capable of, and it encourages us to keep exploring, keep learning, keep pushing the boundaries of what is possible. One of the most profound questions we can ask is, are we alone? Is life unique to Earth? Or does it exist elsewhere in the universe? We do not know the answer. We have not found any definitive evidence of life beyond Earth. But the search is ongoing, and it is one of the most exciting areas of modern astronomy. The discovery of exoplanets, planets orbiting stars other than the Sun, has revolutionized this search. Before the 1990s, we did not know for certain that other stars had planets. But now we have discovered thousands of them. Some of these planets are in the habitable zone, the region around a star where temperatures allow liquid water to exist on the surface. Water is essential for life as we know it, so finding planets with liquid water is a key step in the search for life. But the habitable zone is not the only place life could exist. As we discussed earlier, rogue planets with subsurface oceans could potentially harbor life. Moons of gas giants, like Europa and Enceladus in our own solar system, have liquid water beneath their icy crusts. Life could exist there too. The search for life involves looking for biosignatures, chemical or physical signs that life is present. On Earth, for example, the presence of oxygen in the atmosphere is a biosignature. Oxygen is highly reactive and would quickly disappear from the atmosphere if it were not constantly replenished by photosynthetic organisms. Future telescopes will be able to study the atmospheres of exoplanets in detail, looking for gases like oxygen, methane, or other chemicals that might indicate the presence of life. But finding life is not easy. Even if life exists elsewhere, it might not leave obvious signatures. It might be microbial, too small to see directly. It might use biochemistry different from ours, producing different gases. And even if we find signs of life, we will not know for certain unless we can study it directly. This would require sending spacecraft to other planets or moons, landing on the surface, and collecting samples. This is technically challenging, but not impossible. We have already sent rovers to Mars. We have plans to send missions to Europa and Enceladus, and future missions might be able to bring samples back to Earth for detailed analysis. The discovery of life beyond Earth would be one of the most important moments in human history. It would show us that life is not unique to our planet, that it can arise wherever the conditions are right, and it would raise profound questions about the nature of life, its origins, and its place in the universe. Are there other intelligent civilizations out there? We do not know. The Drake equation, a famous formula developed in the 1960s, attempts to estimate the number of intelligent civilizations in our galaxy. But the equation has many unknowns, and estimates range from 0 to millions. We have been searching for signals from other civilizations for decades, using radio telescopes to listen for artificial transmissions. So far, we have found nothing. But the search continues. The vastness of space makes contact unlikely. Even if there are other civilizations, they are probably very far away. Signals would take years, decades, or centuries to travel between stars. And if civilizations only last for a short time, they might arise and disappear without ever making contact. But the search is still worthwhile, because even a null result tells us something. If we search thoroughly and find nothing, it suggests that intelligent life is rare, and that makes us even more precious. One of the most remarkable things about the universe is its unity. The same laws of physics apply everywhere. The same elements exist on distant planets as on Earth. The same forces shape galaxies billions of light years away as shape our solar system. This is not obvious. The universe could have been chaotic, with different regions governed by different laws. But it is not. It is orderly, coherent, governed by a small set of fundamental principles. This unity is what makes science possible. Because if the laws of physics changed from place to place, or from time to time, we could not make predictions. We could not understand anything beyond our immediate experience. But the universe is consistent, and this allows us to extrapolate. We can study atoms on Earth and know that they behave the same way in distant galaxies. We can study gravity in the solar system and know that it works the same way in galaxy clusters. This unity also suggests that the universe has a deep structure, a fundamental order that underlies the apparent diversity of phenomena. Physicists have been searching for this deep structure for centuries. They have unified electricity and magnetism into electromagnetism. They have unified electromagnetism and the weak nuclear force into the electroweak force. And they are working toward a grand unified theory that would combine all the forces into a single framework. This quest for unity is driven by a belief, or perhaps a hope, that the universe is fundamentally simple, that beneath the complexity of stars and galaxies and black holes, there are a few basic principles that explain everything. We are not there yet. We do not have a theory of everything, but the progress we have made is remarkable, and it gives us confidence that further unification is possible. The unity of the cosmos also connects us to everything else. The atoms in our bodies were forged in stars. The water we drink has cycled through countless organisms over billions of years. The oxygen we breathe was produced by photosynthetic bacteria and plants. We are not separate from the universe. We are made of it. We are part of its history, and we are shaped by its laws. This connection is profound. It shows us that we are not isolated, not alone, not separate. We are part of a vast web of cause and effect that stretches back to the Big Bang and forward into the far future. And it reminds us that understanding the universe is, in a sense, understanding ourselves. There is a tendency to think that mysteries are problems, things to be solved, and then set aside. But mysteries are also beautiful. They are what make exploration worthwhile. If we knew everything, if the universe held no surprises, it would be boring, predictable, lifeless in a sense. But the universe is full of mysteries. Dark matter, dark energy, the nature of black holes, the origin of life, the structure of space-time. All of these are open questions. And they are not just gaps in our knowledge. They are frontiers, invitations to explore. Each mystery is an opportunity to think creatively, to develop new theories, to design new experiments, to push the boundaries of what we know. And when we solve a mystery, when we answer a question, we do not reach the end. We reach a new beginning. Because every answer reveals new questions, deeper and more profound than the ones we started with. This is the nature of scientific progress. It is not linear. It is not a march toward a final goal. It is an ongoing exploration, a journey into the unknown. And the unknown is beautiful. It is full of possibilities. It is where discovery happens. So we should not fear the mysteries of the universe. We should embrace them because they are what make the cosmos interesting. And they are what makes the search for understanding meaningful. The strangest things in space are not just objects or phenomena. They are also questions. What is dark matter? What is dark energy? What happens inside a black hole? Are we alone? These questions drive us forward. They inspire us. And they connect us to something larger than ourselves. We have explored some of the strangest things in space. Rogue planets drifting alone, neutron stars crushed to unimaginable densities, black holes where reality breaks down, dark matter and dark energy dominating the universe, quantum mechanics shaping the cosmos, mysterious signals we do not understand. All of these discoveries challenge our intuitions. They show us that the universe is stranger than we thought, and they remind us that we are part of something vast and mysterious. But they also show us something else. They show us that we are capable of understanding. We can observe, measure, theorize, discover. We can make sense of the cosmos, at least in part, and that is remarkable. We are brief, but we are also extraordinary. We are the part of the universe that can think, that can wonder, that can ask questions and seek answers. And that gives meaning to our existence. Not because we will last forever, not because we are the center of the universe, but because we are here now, and we have the opportunity to explore, to learn, to appreciate the beauty and strangeness of reality. The universe is full of mysteries, and that is beautiful, because it means there is always more to discover, always more to learn, always more to wonder about. So keep looking up, keep asking questions, keep exploring, because the cosmos is waiting, and it is stranger and more wonderful than we ever imagined. Before we end our journey, let me share one more thought about wonder. Wonder is not just about being amazed. It is not just about seeing something spectacular and being impressed. Wonder is deeper than that. Wonder is about recognizing that there is something beyond our understanding. It is about encountering the unknown and feeling both humility and curiosity. It is about realizing that the world and the universe are larger and stranger than we can fully grasp. When we look at the night sky, when we learn about black holes and neutron stars and dark matter, we are experiencing wonder. We are confronting mysteries that challenge our assumptions and expand our horizons. And this experience is valuable. It keeps us humble. It reminds us that we do not know everything, and it inspires us to keep learning, keep exploring, keep asking questions. Wonder is also what drives science. Every great discovery began with wonder. Someone looked at the world and asked, why, how, what if? And then they set out to find answers. They observed, they measured, they experimented. They thought deeply about what they saw. And through this process, They made discoveries that changed our understanding of reality. So, as we conclude this exploration of the strangest things in space, remember the importance of wonder. Cultivate it, nurture it, allow yourself to be amazed by the cosmos, because the universe is full of wonders. And the more we learn, the more we discover, the more wonders we find. Thank you for joining me on this journey through the cosmos. If you enjoyed this exploration, if it sparked your curiosity or deepened your appreciation for the universe, please consider liking this video and subscribing. There are so many more mysteries waiting to be discovered together. Until next time, keep looking up at the stars. Keep wondering. And remember that the universe is far stranger and more beautiful than we ever imagined.